Okay, so let me get. Okay, yeah, thank you very much for that introduction. My name is Peter Siegfried. I'm the postdoc for NERML in the Gameri lab here at GMU. And today I'm going to talk to you about materials discovery, mainly the growth and synthesis of quantum materials and how we pick what materials we want to study. So in NERML's talk, we learned about quantum materials. And in this field, the challenge is to understand the organizing principles that lead to this like complex collective behavior and to explore the range of the applicability of these ideas. Some of these examples are things like charge ordering, the interplay between charge, spin, and orbital degrees of freedom that occur in novel ordered states, and the origin of quantum condensates, which can include spin and charge density waves. Addressing questions in these and other related areas ultimately leads to a deeper understanding of the behavior of electrons, and harnessing these effects has the potential to transform the next generation of electronic materials. In this talk, I'll focus on how we pick and choose the different materials to look for such phenomena. But first, let's look at some examples of what we mean by emergent properties. NERML showed some of these before, and I just want to highlight some of the behaviors that we focus on in our group. In our lab, we focus on the intersection of magnetic and electronic topology. And by this, we mean we look at systems that express unique and sometimes topological magnetism as seen above here. This is an example in, for example, MnSi, manganese silicide. This picture shows how the magnetic moments arrange in the A phase of this material, where these vortex-like structures called skyrmions periodically form in the magnetic texture of the material. In a different material that NERML talked about, yttrium manganese 6 tin 6, here we see the various magnetic phases from this phase diagram, labeled here like DS, TCS, fan-like force ferromagnetism, and schematically pictured on the right. Here, this chiral helix along the C-axis can be modified into distinct phases with applied field, and each of these impart unique properties onto the other behaviors in the material, such as like the electronic properties. And so in a system like this, yttrium manganese 6 tin 6, the material also exhibits topological electronic properties. And so when we talk about these, we mean that the typical conduction and valence bands of the material have linear band crossings. And so these various cones here are representative of such electronic bands. These configurations are seen in many materials of interest, such as topological insulators, where we have kind of an ordinary insulator cone, but then at the surface of the material, there is a Dirac cone-like behavior. And then there's Dirac cones lead to what NERML mentioned as Dirac semimetals, and some symmetry breaking can push Dirac cones into the Weyl semimetal behavior. Looking at materials where both some novel magnetism as well as these interesting electronic structures coexist provides a very interesting playground to study both the nature of these phenomena and how they contribute to and interact with each other. So we now know some features that we're looking for, but how do we pick a material or system to study? And so what do we look for to use as like a guide? Typically, as an experimentalist, we approach this through three main avenues. The first is to comb through theoretical works and look for materials of interest. Novel theoretical papers sometimes don't have material systems with data readily available, but may predict systems where their theories will apply. And as an experimentalist, these are great references to start with, as these new theories require validation. And we, as crystal growers, can produce these systems for testing. Beyond reading many theory papers, looking to specific lattice geometries is a great place to start. As examples, I'll talk about the Kagome net lattices and the honeycomb Kitaev materials. Kagome net systems inherently exhibit topological electronic structures. And here for iron tin, we can see both hexagonal and Kagome layers exist within this crystal structure. And this Kagome layer leads to the formation of Dirac cones and flat band physics in this material. Both interesting topological electronics that we hope to study. Finding a system like this, for example, the rare earth manganese-6 tin-6 systems will contain similar electronic structures from this Kagome net. And this system is of great interest. As you can see here, the choice of rare earth element that goes in this R position can drastically influence the magnetism present in the material. For example, like here, this would be ferromagnetic all in kind of the thickness of the material, whereas with these choices of rare earth ion, you have ferromagnets in the plane of material. Honeycomb Kitaev systems are interesting because these materials are candidates to exhibit quantum spin liquid states. The magnetic interactions between the neighboring ions here, shown in like red, green, and blue, are all different. And the frustration of these moments in this geometry is predicted to exhibit this quantum spin liquid behavior, a novel phase that has been recently just a very of great interest in the field. An example of this type of system is alpha ruthenium trichloride, which beyond the QSL phase has also been shown to exhibit Majorana fermions itinerantly in the material. Looking for systems where similar lattice geometries, as well as these electron and exchange interactions exist, narrows the search for these proposed phases and gives us a great place to start looking by just slightly modifying these types of families of materials. Another way to approach novel materials is to look within a family of materials. One example that comes to mind is the recent discovery of Weil fermions in tantalum arsenide. Weil fermions were first predicted in high energy physics back in, I think, the 1930s. But these fermions were never experimentally observed until their realization in tantalum arsenide recently in 2015. Looking at these elements on the periodic table, we can look at ions that fit within the same family, and we see that they're kind of right next to each other in the same column. So moving to neighboring ions within the same column should have minimal impact on the lattice, the kind of crystal structure, because the only small changes are due to these different ionic radii. But the valence electrons are identical in these systems, producing nearly the same physics. In fact, after the first observation of the Weil Fermi arcs in tantalum arsenide, much work has been done on these variations, niobium arsenide, niobium phosphide, tantalum phosphide, all of which have been shown to be Weil semimetals. And here are just a few examples of some work done by some of our group members, and this middle paper by another group. But this is just a small kind of smattering, but this in the last few years, growing these crystals yourself has put you well ahead of the game in trying to realize these kind of novel systems. In a similar way to looking between the same family of crystals, we can also look at the periodic table to slightly alter material properties. Doping elements replaces just a few percent of one ion for another, altering the chemical potential slightly or the magnetic interactions, but leaving most of the parent compound properties intact. For example, in MNSI, which, as stated before, has this skyrmionic A phase, this A phase only exists in a very small region of the phase diagram. So you can see in temperature and field, this is just a small pocket where this vortice lattice is present. However, if we dope slight amounts of iron in the material to take place of these manganese ions, we can disrupt the properties in a very controlled way and see how that affects this A phase, both the characteristics and the location. Such iron doping leads to significant lowering of the magnetic transition, as well as the size of the skyrmions present, And this is highlighted in these yellow arrows, where you can see as we steadily dope, the transition temperature goes from about 30 Kelvin down to about 5 Kelvin at 13%. And similarly, these skyrmion sizes, the size of these vortices, goes from about 17 nanometers to about 7 nanometers at 13%. However, simultaneously, this doping raises the maximum electronic signatures observed, even resulting in a sign change, as well as affecting the magnetic field experienced by these conduction electrons. This sign change here in this the topological Hall effect that Nirmal mentioned occurs with just only a few percent doping, and then it grows massively up to 13%. And similarly, this gauge field, or the effective field felt by the conduction electrons, is almost 6 times that of the parent compound at only a 0.13 iron, or 13% doping. This shows doping can be an extremely beneficial process to tune and control the material properties and manipulate them in useful ways. And so, although iron doping here resulted in a suppression of TC and enhancement of the topological Hall effect, other options like maybe cobalt or chromium may impact the properties more severely or in the opposite way. And there may be plenty other possibilities and avenues forward. So that's how we kind of pick a system. But once we pick a system, we must now grow the materials for study. And in all of my examples, I've been talking about results that were performed on single crystals. In fact, most of the work of our group is performed on single crystalline samples. But why the emphasis on single crystals? Solid systems can mainly form in 3 ways, and as single crystals, as polycrystalline samples, or as amorphous solids. Amorphous solids are like your glass in your windows, or your windshield of your car. They have no periodic structure, which is the periodicity is a critical ingredient for a lot of the topological electronic properties. And so for now, we neglect kind of these classification of solids. So the difference between single crystals and polycrystalline samples is that single crystals are periodic across the entire volume of the material, whereas polycrystalline samples have very distinct grain boundaries, where the periodicity is observed within each grain, but not between them. Most materials in our day-to-day lives are polycrystalline. The solid block of steel or aluminum in your car, for example, under a microscope, will have very clearly separate grains. Single crystals are very hard to grow and thus are limited in your typical industry and commercial applications. However, there are many big advantages to using single crystals. In general, the material properties are oftentimes dependent on the crystallographic orientation, i.e., what direction along the crystal you are looking. For example, applying a magnetic field along some of these red arrow directions should yield effectively the same results, as here these red arrows are lying on the same type of repeating ion. This kind of periodicity has this rotational symmetry, and you expect kind of this behavior, this pattern going through the center of these ions is identical to the pattern going through the center of these ions. However, this blue arrow, you can see it kind of cuts through the center and then splits in the center. The pattern is distinctly different from the reds. And this you expect that with this different ion arrangement, this should yield different properties. In a polycrystalline sample, however, one crystal direction cannot contain grains of both periodicity orientations. Drawing a line across this sample, for example, it sees grains with both this kind of blue and red orientations. Thus, we expect the results from for measurement performed in this crystal to kind of have a muddled result that's like the average between both of these orientations together. In order to isolate the orientation dependencies and fully study the physics involved in these systems, this single crystal is necessary for us to have. So to get these single crystals, there are many methods for growing them. And these include chemical vapor transport, flux method, floating zone growth, Bridgman technique, molecular beam epitaxy. But in our group, we perform chemical vapor transport and the flux growths. And so I'm going to go in depth and focus on those. So in chemical vapor transport, typically solid components are volatilized in the presence of a gaseous reactant. And this gas is called the transport agent. And these volatilized solid components are picked up and then deposited on the other side or elsewhere in the form of single crystals. The video here is showing the process where the elemental components of the desired material, this red and blue, are sealed in a quartz tube with the transport gas, this yellow-green gas moving back and forth. And this transport is governed by two processes, convection and diffusion, due to this temperature gradient we apply on the tube, going from T1 to T2. T1 is usually hotter than T2, but this is dependent on whether the reactions are endo or exothermic. As this gas circulates slowly, it picks up some of the material and then deposits at the other end, and this repeats, essentially building these crystals bit by bit and layer by layer. For this process, the material components must be volatile with the transport gas, and typically for us, this is an iodine transport gas, but some processes require bromine or chlorine compounds. And these quartz tubes are required to be sealed under vacuum. And this prevents contamination from things like oxygen or nitrogen that might react with our gas or contaminate our samples in some other way. Some elements or materials may not work in the CVT method, as the volatility with the reactant of the composite elements needs to kind of match and be in the same kind of temperature range. And so although only a temperature gradient of 100 C or so is necessary, the base temperature is always high, somewhere around 1000 C, 900 C. So our gradient might span 1050 C to 950 C in order to get this reaction to take place. For compositions where this is not possible, we instead use the flux growth method. The flux method is quite different from chemical vapor transport. The composite elements are placed within a crucible, shown here in the bottom left, along with the flux. And this whole crucible structure is then sealed within a quartz tube under vacuum. Upon heating, the flux melts first, and all the components, all these bare elements, will dissolve into the flux, into the melt. And then you have a homogeneous melt here at some high temperature. As we slowly cool this crucible, single crystals begin to precipitate and kind of nucleate out of the melt. And these crystals then form within the crucible. And after the growth is complete, usually taking about a week, maybe two, and while this crucible is still hot, so the flux is still molten, we pull it out and centrifuge it inverted. So that way all the flux gets pushed out to one side, leaving just our nice grown crystals on the other end. The mesh here is just in place. It has no use in the actual growing of the crystals, but it's used to separate out the flux at the very end of that centrifuging stage. For this method, we are dependent on the alloying phase diagram of the specific material, and there's quite a bit of chemistry that is going on here. For example, if we wanted to grow, let's say, iron 3 gallium 4, we would first need to ensure that the iron and gallium are soluble in our desired flux. For example, we use tin. Once that is confirmed, we would need to ensure that we start our growth somewhere in this region. Around 65% gallium with a temperature of about 1100 to 1200 C. Upon cooling, when exiting the liquid phase here, the only solid phase that's stable would then be in this iron 3 gallium 4 column. And this would give us our desired material using this method. However, if instead we wanted to grow something else like the iron, I think it's 28 gallium 12, that was somewhere lower temperature that might be below our flux melting temperature, this would be impossible to measure here. or impossible to make because our flux would solidify prior to our precipitate forming. And this would be a very tricky situation. So making sure that your phase diagram and your flux chosen and all these things are compatible is a lot of the work that needs to go into performing this kind of flux growth method. So here's some examples of our growth furnaces and the crystals that we produce. Nirmal has showed some of these pictures in his talk, but here I show the actual tubes, the quartz tubes that we're sealing, and these are about a little over centimeter and a half. I think they're 15 millimeter diameter tubes, and about 8 inches long. For CVT, these go horizontally in the tube furnace, and we are able to apply the temperature gradient to get that CVT process occurring. Here's a tube sealed for flux growth, and you can see at the bottom the crucible, and you can see kind of some of the elements poking up out of the top there. And the quartz wool here is our mesh that'll help kind of sieve the crystals from the flux during the centrifuging step. These tubes are placed vertically in the box furnaces, as in this case, we don't want to transport any of the material. We want it to melt in the crucible. And so this is how that growth process is taken. These methods, both of these methods can produce very high quality crystals. And you can see here, even just in the pure growth, you can sometimes see what the kind of unit cell structure kind of taking place, where it be it cubic or like hexagonal. This is maybe tricky, but there's about half a hexagon here. You can see this about angle. So this is very evident about what you can clearly see that these are these are high quality crystals. They're big, they're nice, fantastic to work with. So that's kind of the growth procedure. And now that we have the materials in hand, Nirmal talked about a lot of the data or some of the data that we've collected in our lab. And I just want to briefly mention some of the things that we do. Some of the first steps that we take is the initial characterization, the X-ray diffraction, or we can even send the crystals out for neutron diffraction. So whereas X-ray diffraction will tell us about the crystal lattice, the neutron diffraction can actually probe directly the magnetic structure of the material. Although that's a trickier measurement, and we like to do some of the other property characterization prior to neutron diffraction. Some of the first things we always do is characterizing the temperature and magnetic field dependencies of the sample. So we'll sweep temperature or sweep magnetic field and measure things like resistivity or heat capacity or the magnetization to see if we can find the various phase transitions that are present in the material. We can also submit the materials to extreme conditions, and then this helps us isolate one or more independent variables and probe this material behavior directly. Some examples of this are going to extremely low temperatures. If we reduce the temperature to near the T=0 limit, this completely wipes out lattice vibrations and things like phonons in the material, and allows us to view quantum phase transitions as we change other variables such as pressure or doping or magnetic field. Another thing we can go to extremely high magnetic fields. And this gets rid of the magnetic dependence. And so we can fully saturate and polarize our magnetization in our material. And this gets rid of things like spin fluctuations or the kind of magnetization dependence, giving us a background for what the material is doing without the magnetism. And this is a really nice way to compare to what the magnetization is doing to the material properties. And the last one I'll mention is just strain or pressure studies. These are when you're actually pushing on or stretching the physical crystal. And this helps us understand how the lattice itself, this periodic ion arrangement, how do the material properties depend on what that ion spacing is? So I'm now going to plug our group for a bit here in the Gamiri lab, headed by Nirmal. Although my talk focused on the synthesis, as Nirmal said, we are both a synthesis and a characterization lab. And so here's the link to our website where you can learn a lot more about the work that we're currently doing, as well as our recent publications. The group here, it consists of myself, the PI, Nirmal, and our grad students, Connor Jones and Hari Bandari. Half of our lab is dedicated to the growth and synthesis, and we have multiple box furnaces for flux growth, as well as a few tube furnaces for CVT, although those aren't pictured here. These growths can take up to 2 weeks, and so having many furnaces is extremely beneficial and allows us to constantly cycle our growth schedule. And as I stated before, all our growth occurs in sealed quartz tubes under vacuum. As the melting temp of quartz is about 1700 C, we have to use a hydrogen oxygen torch that can get up to 2300 C, which is quite hot. And here you can see Hari sealing up a tube in order to prepare a flux growth, I believe, that is now, I think, in the oven. Once we grow our crystals, one of the first characterizations we perform is X-ray diffraction. An R diffractometer allows us to quickly check the phase of the crystal structure of the crystals and ensure that the growth is actually what we want. Sometimes these growth procedures don't produce what you want, and sometimes for very odd reasons. One of my favorite growth stories is of a professor who was trying to get a batch to work, but could never quite get it right. The crystals always failed. Their student, however, would nail the growth every time. And so one day the professor decided to stand next to the student and copy each step exactly. And they performed the growth simultaneously. And still the student's crystals were great, but the professor's not so much. So after checking every variable, they finally found the difference. The student's furnace was on a desk that had a heavy drawer. And other people opening and closing the door and slamming that drawer agitated the tube in that furnace and helped the growth. And so I always say, you should take notes on everything, the weather, your mood, because who knows what will be important for a good growth. This is really where kind of the art of crystal growing comes into play. And so with this machine, beyond checking that our crystals are of the correct phase, we can also set this up to use to check the orientation of our crystals. And this is extremely important for allowing us to control exactly what direction we're applying our field and our currents and our heat during our measurements. And then finally, just on the properties characterization, we have an amazing machine in our lab that can handle a very wide variety of measurements. And this is the Dynacool PPMS. This can reach a field strength of 9 Tesla. And for reference, the Earth's magnetic field is about 30 micro Tesla. Some of the strongest neodymium magnets that some of you may have held in the past are only a few tenths of a Tesla. So 9 Tesla is quite large in such a versatile space. We can also accurately control temperature from 1.8 to 400 K, and this gives us an extremely wide range to test the various phase transitions at intermediate temperatures, as well as get very close to that T=0 ground state. And we can run everything in this machine from electrical resistivity, heat capacity, thermal transport, and even magnetization measurements, all in this system. It's very, very useful and very productive in our group. So thank you for attending my talk. I'd be happy to answer any questions, and I invite you to check out our website for more information about the great work we're doing in our group. Thank you.
Thank you, Peter. Great talk and very handy. Do you have any questions? If you have, please directly mute yourself and ask.
Could I ask a question?
Yeah, please.
Could you tell me how hot the furnaces can get? What's the max temperature on them?
Yes, I believe the tube furnace we can maxes out at 1100 C. The box furnace goes up to 1200 C. And that's kind of the maximum. I think that limit is the heating coils and the thermocouples. Thermocouples will tend to burn out the higher temperature you go, and then that just reduces the lifetime. But I think there's safety precautions in there where you don't want to overload the furnace. But 1200 C is quite a bit.
Is that standard? Is that like low for the kind of work that you're doing, the research that you're doing, or is that more of like a average
Well,
temperature that these kinds of furnaces should reach for these kinds of research
oh yeah,
purposes?
so these furnaces are, you know, commercial products. They are that's standard for these furnaces, and it's also fairly standard for these growth procedures too. Because a lot of the like flux method growths, your flux may go molten at 600, 650, maybe, or maybe even lower. And so you might not even need to use the full range up to there. Sometimes we can get away with growths at 700 C, or maybe it only maxes out at 800 C. You know, we don't have to use that full range. Now this is different than, I think, some of like the floating zone methods. Which we don't do in our group, but some of those might need to get higher. But that's usually only at like a single point. It's not like within a furnace. So yeah. So for our purposes, these are standard and these are great. But for maybe a different, if we wanted to do different techniques, we would need more equipment.
Okay, thank you. I appreciate it.
Yeah, thank you for the question.
I did have one question too. You mentioned that you used an oxygen something kind of torch to heat. What did you say that was? Can you talk about that a little bit?
It's just it's a hydrogen oxygen torch. And so it's quartz is, and the quartz we get kind of pure silica quartz. It has just a very high melting temperature. And so a lot of glass blowing will be done with just like a propane torch or a butane torch. But we require a hydrogen oxygen mixture to burn hot enough to melt the quartz. It's just yeah, it's just we have a big old hydrogen tank, big old oxygen tank. It all feeds into, you know, this handheld torch. It's kind of cool. It's the most dangerous piece of equipment in our lab, but it's neat to use.
How hot are you guys burning with it? It's kind of interesting. I've never heard of this kind of torch before.
Oh yeah, well we're burning it fairly hot, but that's in order to melt the quartz. We're probably only hitting about 2000 C. It should get up to 2300, but the very hot kind of cone of the torch is maybe 2000 C.
Okay, thank you.
Yep, you're welcome.